it's a good point to bring that up, and we can have really what we may call complicated pulses, but natural. One can shape the polarization of the instantaneous polarization of the wave as well. That is possible. Just like we pass a linearly polarized wave through a wave plate and get a circularly polarized output, one can play tricks to shape even the local polarization in a seamless way and produce really complicated pulses. Okay. Right now we are not talking about such pulses, but they can be of even of scientific utility. Okay. So, what does the let us move on from phi 0 to phi 1, right. So, this discussion is about phi 1. The next term in the description of these pulses, both in the frequency and the time domains. Okay. So, the shift theorem of Fourier transforms tells us the following, right. So, if I take a quantity, if I take a function phi of rather f of t, whose Fourier transform I know to be capital or uppercase f of omega, then if I shift the time axis by a quantity phi 1, right, if I shift the time axis by a quantity phi 1, then of course phi 1 should have units of time, which it does, isn't it? Okay. The first order, this is first order phase in frequency. So, this is phi 1 in the omega domain. Let us also remark that this is phi 1 of omega, which is group delay, right. Then this thing essentially okay, sorry, this is the phi 1 we are talking about. This is phi 1 of omega. This, it is the same phi 1 because it has units of time, but I should start from here. This is group delay. So, this term in the frequency domain, okay, essentially if non-zero. Why if non-zero? Because if it was 0, we would have just f of omega, the Fourier transform of just f of t without this phi 1 present there mathematically would have been the pulse with just a non-zero phi naught and nothing else, no other Fourier coefficient appreciable in its value. But if we have phi 1 non-zero, but phi 2 and others higher orders 0, then essentially by the shift theorem on Fourier transforms, we have in the frequency domain a scenario where the lower order term, which is f of omega, is multiplied by exponent of I omega phi 1. So, assume that we measured this in the frequency domain. We measured say y1 square root, we measured s of omega and we measured phi of omega, which we realized has non-zero phi naught plus a phi 1 times omega plus 0 for the higher order terms. Then if I want to reconstruct the pulse from the frequency to time domains, because I have measured both the s of omega and phi of omega, I have all the information needed to reconstruct the pulse back in the time domain. We would then reconstruct this same pulse as before, I mean same pulse as the one where phi 1 was 0, but it would be shifted in the time axis by an amount minus 20 femtoseconds. Or if phi 1 was negative, if phi 1 was something less than 0, we would have measured, we would have essentially had this to be shifted in the positive direction by the same amount. If phi 1 was, sorry, in this case phi 1 is minus 20. If phi 1 was plus 20 femtoseconds, if phi 1 was plus 20 femtoseconds, you would have had the pulse to have been shifted in the positive time side, right. So, how do we make sense of this thing, right? How do we make sense of like this positive versus negative group delay? So, we can always think about it like this. So, suppose I took this pulse and put it through a beam splitter, say 50-50, which reflected the pulse up and I retro reflected it back somehow like that, maybe like in a real laboratory setup. Let me use a different, say blue for this. Another pair of mirrors. Which again reflected the pulse back. So, what is this? This is a classic Michelson interferometer, right. So, now the pulse which came in as whatever, there is a dark blue pulse and there is a light blue pulse if you wish. And on this axis, it is a matter of choice which I consider my reference. As a consequence of doing whatever it took to produce this delay, the delayed pulse could have either been ahead or behind my reference. All that depends upon the relative length for path here. Let us call this path 2 versus path 1. So, if this had a length L1, this had a length L2, a relative delay is captured by this. Of course, this is I am just giving a way in which to produce a delay, okay. But one can also think of a scenario of the following type, okay. Suppose a pulse propagates along the z axis or z axis, and in its path we have some medium. I had a reference pulse, in which case I sent this through air or vacuum, it is air on either side. I sent this through a hypothetical volume which was filled with air, and next I introduced a slab of glass before the pulse entered this volume of glass, which say has a thickness. What symbol should I use for thickness here? Let us say D. Now, glass has a refractive index of about 1.5 for the wavelengths that I consider, and let me also assume that this refractive index is the same across the range of frequencies where the pulse has appreciable spectral amplitude. Then if I let these two pulses run through, or maybe I could say I conduct, ouch, okay, anyway, let me do that again. Or a better example. So, this could push me to do a better example, give you a better example, that is. So, one half of this glass, let us say the other is, we can make it water, fish tank. Let us make this a fish tank. So, these two pulses were in a race, this guy and this, since Z is the propagation axis, right. So, these two pulses propagate through the same, like here, and then I take a snapshot of these two pulses. The one that had the benefit of propagating entirely through a lower index medium would be ahead of the other, and this Z is also a measure, this delta in the Z is also a measure of time. There will be a delta in the time, and that time, delta in the time is the group delay, TGR or phi 1, right. So, this term becomes appreciable when we consider propagation effects, but note, and with some foresight, the important fact that phi 1 and highlight phi 1 does not affect the instantaneous frequency. What does this mean? In again with a little bit of foresight, what we can also appreciate is the following, that despite my very limited sketching skills, these two pulses look fairly alike. So, you can give me at least a pass grade on that, right, the dark blue and the light blue ones. But in other words, when we say that the instantaneous frequency has not changed, what we are trying to say is if it started as a nearly Gaussian pulse, the medium did not, the medium did not do the following to it. If I may choose another color, the medium did not distort its shape. It need not have suffered any loss or anything, as we will see later. With just phi 1 in this context being non-zero, if phi 2 and others are indeed 0, this does not happen, no distortions. But we can anticipate something already very nicely over here, right. That is already an insight knocking on our doors to see, because what did we consider here? We considered the fact that there is a refractive index n, which let us say is 1.5 and it was exactly 1.5 for all omega, and this led us to a delay, right. This led us to a group delay, and while it kept all the other terms in the spectral phase expansion phi 2 and others 0. But what is phi 2? What is phi 2? Phi 2 is d omega of phi 1, it is the variation in of phi 1 with frequency, or the dispersion of phi 1, the delay, the dispersion of group delay. The dispersion of group delay would be non-zero if n indeed depended on omega. That is, refractive index was dependent on frequency, which it always is, and it should be appreciable enough. So, if we had conventional simple dispersion, the fact that we can learn from here is that we will go away from the no dispersion, no distortion scenario. Dispersion will distort a pulse. At least I can learn that from this little exercise. How exactly is a matter of detail, which is in the information contained in phi 1, in phi 2. That will depend on dn by d omega, or d phi 1 by d omega will determine the nature of distortion. We can also extrapolate and say, hey, what about the dispersion of phi 1, that is the second order dispersion, d2 phi 1 by d2, d2 phi 1 by d omega 2, right. What about this? Why stop there? What about the third? What about the higher order derivatives, and so on and so forth? So, in that sense, this is a good place to set the notion that the higher order phase terms are going to do something to the shape of not E, but the envelope, not the electric field, also of the electric field. I would say the phi 1 itself starts doing things to the shape of the electric field, but that is a matter of detail. I will not go there now, I will recall this later, but talking only about the envelope, that is the square root of I of t in the time domain, right. Sorry, we should call it, should have made it phi 1. The dispersions of the first order, the second order and third order of phi 1, okay, these terms are going to lead to pulse distortions, and it is inevitable because this is always true. N is a function of omega. So, pulses travelling through media will absolutely get distorted. Air has a very weak dependence of n over omega as compared to glass, but that is trivial because the n of air itself is significantly much closer to unity, that of vacuum for this very classical consideration, right. Whereas for glass it is 50% different from that for air. 1 becomes 1.5 as against 1 being 1.001 or something like that for air at normal temperature and pressure. So, therefore, any dispersion in air would be quite small, okay, whereas for a piece of glass it will indeed be appreciable, and so a short pulse propagating through glass will get distorted.